Now that we understand how to calculate mean, variance, and standard deviation for a normal data set, we want to talk about the equation of the probability density function of the normal distribution. So this function, f of x, is the standard form of the probability density function for a normal distribution. Notice that it relies upon the standard deviation given here by sigma, we also see it here, and the mean mu, which we see here. So in order to build the equation for the probability density function, we need to have the mean and standard deviation that we learned to calculate earlier. So let's say, for instance, that we had from our data set calculated a mean of 5 and a standard deviation of 3. Then we could plug these values into the probability density function, and we would get 1 over 3 times the square root of 2 pi, and then Euler's number here, raised to the negative 1/2 power, multiplied by x minus our mean of 5, so x minus 5, all divided by standard deviation, so 3, quantity squared. And now we have here the equation for the probability density function of the normal distribution that has a mean of 5 and a standard deviation of 3. Now, we talked about earlier how a normal distribution was a bell-shaped curve. Well, here are some examples of these probability density functions we've been talking about. In fact, this distribution in green here is the distribution for the normally distributed data with mean 5 and standard deviation 3. In red, we have a mean of 5 and a standard deviation of 2, and in blue, we have a mean of 5 and a standard deviation of 1. We can see that the mean is 5 for all three distributions because we see here that all three distributions are centered at 5. Remember that for any normal distribution, the mean is right here at the center of the curve. And for any normal distribution, this is also where we'll find the median. In other words, in a normal distribution, the mean and median are always equivalent. Now, what we notice is that the curve, the graph of the probability density function is of course just dictated by these two values, the mean and the standard deviation, because those are the only two values we need in order to plug into this formula for the probability density function. And that's why we can express any normal distribution as just its mean and standard deviation, or what we actually use for our standard notation, which is variance, of course, just the square of standard deviation. So whenever we're dealing with any normal distribution, we will often just express it this way, the normal distribution of the mean, comma, the variance. And so instead of having to express this entire probability density function or give extra information or a sketch of the curve, all we have to do is say we're dealing with the normal distribution 5, 1, and that indicates a mean of 5 and a variance of 1. Here we have a normal distribution with a mean of 5 and a variance of 4, and here we have a normal distribution with a mean of 5 and a variance of 9. Now we always give the variance, but of course we know that standard deviation is just the square root of variance. So based on these expressions of these three normal curves, which correspond to these three curves that we already sketched, we know that the standard deviation here is 1, 2, and 3, the square roots of 1, 4, and 9 respectively. So just from this notation here, we can immediately see mean, variance. We can take the square root of variance to get standard deviation, and then we can use this information to plug into the equation of the probability density function for a normal curve and use that equation then to sketch the curve. If we graph this equation after we've plugged in the mean and the standard deviation, we will get this picture of the normal curve. Let's notice again here too that as the variance and standard deviation increase, the normal curve gets flatter and wider. And that's because variance and standard deviation are measures of spread. And so when we see a higher value for variance and therefore a higher value for standard deviation, that means the data is spread out further from the mean. The data gets pushed out further away from the mean to both the right and left, as opposed to when variance and standard deviation are smaller and we see more of the area under the curve, more of the data pushed closer to the mean on the right and the left-hand side. That data is pulled in toward the mean, and so we see the curve rise up and become taller. That normal curve is taller, the data is more tightly clustered around the mean, the spread is smaller. But as long as our data creates this symmetric bell shape following this form of a probability density function, we know that we have normally distributed data, regardless of whether the curve is taller and more narrow, like this blue curve, or shorter and wider, like this green curve. Now, that being said, let's talk about one of the most important conclusions we can draw from a normal distribution, and that is breaking up the area under the curve into 1, 2, and 3 standard deviations around the mean. So here we have a normal curve. We have the mean here at mu, and we've separated the area under the curve based on standard deviation. So this value right here, mu plus sigma, means the mean plus 1 standard deviation, whereas mu plus 2 sigma here means the mean plus 2 standard deviations. So here, for this green curve, we said that the mean was here at 5 and that the standard deviation was 3. So 1 standard deviation above the mean has to be 5 plus 3, or 8. So we see that here at 8. And then 1 standard deviation below the mean has to be 5 minus 3, or over here at 2. And so we can see for this green curve that we have the mean here, and then this is 1 standard deviation below the mean and 1 standard deviation above the mean. Contrast that with this blue curve here, where we see the mean at the same value of 5, and then we said that standard deviation was equal to 1, which means 1 standard deviation above the mean of 5 has to be at 6 here, and 1 standard deviation below the mean has to be at 5 minus 1, or 4, right here. So we have 4 and 6, and we can say that for the blue curve, an interval of 1 standard deviation around the mean ranges from 4 to 6, whereas for the green curve, an interval of 1 standard deviation around the mean ranges from 2 to 8, a much wider interval for 1 standard deviation around the mean, which of course makes sense because we know that for the green curve, the data is more spread out. Variance and standard deviation are larger. That measure of spread is larger. The data is more spread out away from the mean, whereas for the blue curve, the data is more tightly clustered around the mean. We see that smaller standard deviation. So for the normal distribution, we're particularly interested in these intervals that define 1 standard deviation around the mean between mu minus sigma and mu plus sigma, 2 standard deviations around the mean between mu minus 2 sigma and mu plus 2 sigma, and 3 standard deviations around the mean between u minus 3 sigma and u plus 3 sigma. Because what we know to always be true for normally distributed data is that 68% of the data will always fall within 1 standard deviation of the mean, and because the normal distribution is always symmetric around the mean, that means 34% of the data, or we could also say 34% of the area under the probability density function under this curve, or 34% of the probability has to fall between 1 standard deviation below the mean, and 34% of the probability or the area under the curve has to fall between the mean and 1 standard deviation above the mean. We also know that for every normal distribution, about 95% of the area under the curve will fall within 2 standard deviations of the mean, and that about 99.7% of the area under the curve, or the probability, will fall within 3 standard deviations of the mean. These numbers, this idea, these percentages, are called the empirical rule, or more blatantly, the 68, 95, 99.7 rule, given by these values, 68, 95, 99.7. But the empirical rule is what tells us that for every normal distribution, for every set of normally distributed data, for every probability density function representing a normal curve, anytime we have this bell-shaped curve that is normally distributed, then we can always break up the area under the curve based on these percentages, which allows us to answer all kinds of probability questions. For instance, with this information alone, if we know that our normally distributed data has a mean of 5 and a standard deviation of 3, going back to this curve that we started with here, and we want to answer the question, what is the probability that a randomly selected value in our data set will fall between 5 and 8, or will have a value between 5 and 8? Well, we know that the mean is 5, and that the boundary here of 1 standard deviation above the mean is 8. So the probability that one randomly selected data point is going to fall between 5 and 8, that's just this particular section of the normal distribution. And we know that 34% of the area under the curve falls within this interval. And so we know right away that there's a 34% chance that a randomly selected value from our data set will take on a value between 5 and 8. And of course, we can use these percentages in an infinite number of other ways. So take this same data set. What's the probability that we get a value less than 5? Well, 5 is the mean, and in a normally distributed data set, 50% of the data is below the mean, 50% of the data is above the mean. So the probability of getting a value less than 5 is 50%. The probability of getting a value greater than 5 is also 50%. The probability of getting a value less than 11 for this normal curve here, the mean is 5, the standard deviation is 3. So one standard deviation above the mean is 5 plus 3 equals 8. Two standard deviations above the mean is 8 plus 3 equals 11. So 11 is two standard deviations above the mean. 11 puts us right here at two standard deviations above the mean. And so to find the probability that we get a value less than 11 would just mean that we add up all of these probabilities, starting with 13.5 and then 34, 34, 13.5, and 2.35. Or how about the probability that we get a value outside 3 standard deviations around the mean? Well, we know that within 3 standard deviations of the mean, we have 99.7% of the area under the curve, which means the area outside of 3 standard deviations is 0.3%. If we divide that by 2 to put half of that area into each tail, we see these values right here. So instead of the total area in these two tails being 0.3%, in this upper tail here, we have 0.15%, and in the lower tail here, we have 0.15% of the area outside of 3 standard deviations away from the mean. And that 0.15% captures all of the area under the curve infinitely out to the left here and then infinitely out to the right here. So within 3 standard deviations of the mean, we have 99.7% of the area, 99.7% of the probability. This 0.15% in each tail captures everything else as far as this tail goes out to the left or as far as this tail goes out to the right, everything outside of 3 standard deviations. So then, for instance, if we wanted to say, what's the probability that we get a value less than 11, going back to this normal curve here with a mean of 5 and a standard deviation of 3, well, if our mean is 5 and then one standard deviation above the mean is 5 plus 3 or 8, then 2 standard deviations above the mean is 5 plus 6 or 11, or 8 plus 3 equals 11. So we know that 11 for this curve puts us at 2 standard deviations above the mean, which is right here. So the probability that we get a value less than 11, all we have to do is add up all these percentages, 0.15, 2.35, 13.5, 34, 34, and 13.5, or to take the easier route, since probability always sums to 100% or 1, we can just take 100% and we can subtract from that this 2.35% value and this 0.15% value, and we get a result of 97.5%, which tells us that we have a 97.5% chance of finding a value less than 11 given this normally distributed curve with these properties, a mean of 5, a standard deviation of 3. It's this idea of the empirical rule and these standardized percentages, because the normal distribution is a standard curve, that's going to allow us, as we continue on here, to answer all kinds of probability questions and then even start doing some statistical analysis on normally distributed data, which ultimately leads us to an idea about significance, being able to start with a hypothesis, run an experiment or collect data, and then determine the significance of the result of that data to determine how unusual it is to find the result that we did. We'll talk all about that when we get to hypothesis testing, but the idea here is that this normal distribution we see over and over and over again in real life, and almost more importantly, even when we collect data and we determine that it's not normally distributed, we'll learn about a way that we can sort of change that non-normal data into normally distributed data so that we're able to use this normal distribution and all of these probability figures that go along with it. And so, because we'll be using this normal distribution over and over and over again for normally distributed data and even non-normally distributed data, it's critical that we understand this idea of this symmetric, bell-shaped normal distribution where the empirical rule can give us the likelihood that a particular data point falls within some certain standard deviation interval around the mean.